All right, we are live, everybody. Welcome to the 21st installment of the Local First Meetups. Uh, I'm always excited because it's always a fantastic set of speakers. Today we have Felicia, Sahil, and Jishwan talking to us. And first up, we have Felicia, who is from Jamsocket, ready to talk to us about some of the awesome work they're doing. And for a little bit of context, founding engineer, got to meet her in San Francisco, lovely person. And if you're at the Convicts Local First, you've already got the sort of preview of the talk. So without further ado, I'll hand it over to you, Felicia.
So, share my screen. Great. Thanks for the intro. And hi, everyone. Excited to be here. Today, I'll be talking about YSuite, our open source YJS sync server. It has built-in persistence to object storage, and it's one of the fastest ways to bring real-time collaboration to your app. And today I'm going to be chatting about how you can do that in a way that allows you to easily access other local first features like offline editing. Um, Before we dive into YSuite, I just want to give some background as to why collaboration matters for local first applications. So I'm sure many of you all are familiar with Ink and Switch's article on local first. When they coined that term, they espoused 7 ideals for local first, um, inspired by the applications that we've used every day, like Google Docs, Linear, and Figma. And for those applications, the cloud was really what enabled seamless collaboration. And the big question for local first is, can we do that without dependency on the cloud? And can users retain ownership over their data or collaborate offline? Today, I'm going to be focusing on collaboration specifically for documents and explore how tools like YSuite make it easy to build that in a local first application. And you can think about a document as a text editor in a Google Docs or a design file in a Figma application. It essentially represents some text or JSON shaped data. So why JSON shaped data? CRDTs are kind of essentially JSON shaped, and CRDTs are kind of the data structure for collaborative applications, according to the Ink and Stitch article. And in this diagram, we have a to-do list. And when a client makes an edit to that to-do list, it gets synchronized in the server and sent back to the client so that both clients have the same source of truth. And there are many different CRDT implementations out there. We're going to be hearing about Loro very soon. For YSuite, we use a CRDT called YJS. And we chose to build our first sync engine on YJS, largely because it offers a very simple API and has a really rich ecosystem with bindings to text editor components and different persistence and hosting options. So when you're building a collaborative component with YJS, what you're doing is you're creating a YDoc with shared data types like the YMap, YArray, and YText. To give you a concrete picture of what that document looks like, I'll show you an application that we recently built. It's kind of like a Google Docs clone. Can you guys see the screen change, or it's the same? Okay, so you're seeing this like document
Yep.
here. This text editor is built with Slate's rich text editor. And when I'm typing, that content gets synchronized and persisted with the YSuite server. So if I make this document public and I open it in a new tab, I should see the edits that have come so far, and then I can also contribute. So that's kind of the document. And how is that built? On the client side, you can basically use YJS's shared data types with the YSuite React hooks. So here In a more simplified application, if I'm just creating a shared toggle, I have a use map, and when I change that value, it gets synchronized and persisted. How it works is we wrap the collaborative application with a YDoc provider, and that YDoc provider authorizes a user to a doc and pulls the doc itself from the YSuite server and loads it to global state so it can be accessed by its child components. Architecturally, what that looks like is um, when the application first loads, YSuite pulls the doc from S3 and sends that to the client. So both clients have, or whichever clients are connected, have a copy of that YJS document. When they make edits, those edits are sent back to the YSuite server and persisted. What's missing in this kind of graphic is the platform that's hosting and deploying YSuite Sync Engine. And one thing that what we've recently released in the past few months is the ability to run the YSuite server on JamSocket. And JamSocket is essentially WebSocket infrastructure inspired by the infrastructure that powers Figma and Google Docs. And what's really cool about JamSocket is you can run any sync server. So we have a customer that actually runs Loro on JamSocket for a collaborative spreadsheet. As for YSuite, why did we make kind of object storage kind of the first class storage option? For us, we really believe that object storage is the perfect kind of like standard for document-based applications. This is because of the way users interact with these kind of applications. If you're kind of working on a Figma file, you're kind of editing and collaborating actively. And then once it's done, you leave that document in archive. So object storage is very cheap for that kind of user interaction. So Figma actually does use object storage to store their documents. And so we offer a managed storage option, as well as a way to connect your own AWS S3 bucket. Another advantage of object storage is it allows us to store the full history of a document instead of just the latest version. And that history feature is something that we're coming out with on the open source YSuite side in the new year. So stay tuned for that. Lastly, I'll share this project that was built by Jake Lazaroff, who recently joined JamSocket. And prior to him joining, he worked on this really cool app that was inspired by an Ink and Switch local first case study. The project is a travel planner where you can use a text editor here on the left to kind of plan your travel, and then those locations get mapped onto a kind of map on the right. And one of his big goals was to make the unstructured data like text as important as the structured data. So this application waypoint uses YSuite for collaborating on that text editor, and it also uses YIndexedDB from the YJS ecosystem for offline editing. And that's kind of what we really love about YJS is the kind of plug and play nature of the ecosystem, and that you can utilize multiple tools to really build your local first application. So I highly recommend checking out this project as kind of a local first case study. The kind of goal of the application was to show that you can definitely build local first applications today and meet a lot of those 7 ideals. If you guys are interested in talking about local first in person and you happen to be in London on December 5th, we are hosting an event called Local Thirst with TL Draw at their office. So you can check that out on Luma. And if you want to tune into future events that we host in person, you can follow us at JamSocket HQ. And if you're interested in building your application with YSuite, find us on jamsocket.com/YSuite. And that concludes my talk.
That's awesome. Drop the link into the chat so that other people can get on the program. There's one thing that I really love about local first and just the community as a whole is this big tent approach where competitors are rooting for each other. Somebody else mentioned it at the meetup last week in San Francisco at Convex offices. And it's really true. Like even dropping the Laurel bit in the slide, and it just keeps happening, and it's a recurring theme with everybody believing that the pie is just so much larger than what it is right now, and that we can all work to make it bigger instead of expanding our own slices. Next up, we have Sahil. He's a student at my alma mater, Purdue University, and he's working on something that I've been really interested in for a long time, and that is about getting all my data and having it be useful to me. So I'm excited to hear his talk. All right, over to you, Sahil.
Hey guys, I'm Sahil. Thanks for the introduction. I'm building an open source framework called Surfer Protocol, and let me just share my screen real quick. Uh, Perfect. Um, Yeah, so Surfer Protocol is just all about exporting and building applications off your personal data. So for some more context for myself, I really got into building things around 2 years ago when ChatGPT came out. I remember coming up with all these crazy ideas and all these cool things I could do. So me and a few friends tried building literally any AI thing imaginable. We tried building an AI web browser, chatbots, and even a Discord bot. But time and time again, what we noticed was that these these things were only as good good for us as the context they had about it. And that came in the form of personal data. And we didn't want to give these AIs our entire life story when all this data about us exists on the different platforms we use, like Notion, Twitter, LinkedIn, etc. But getting that data is super hard, and big tech has never had any incentive to get that data back to you. Only very recently with GDPR and DMA has exporting been happening, and that exporting is still a pain. Like for LinkedIn, I think you have to wait a day, and it's not even one full export. It comes in the form of multiple exports. Um, and right now, these companies want to all make an AI out for you. Like Apple has Apple Intelligence, Notion has Notion AI, et cetera, et cetera. So that's where something like Surfer Protocol comes in. So a local first open source framework that allows you to get that data and do what you want with it. So if you want to build your own personal private AI, you should be able to do that. If you just want to hoard all your data from big tech because they keep deleting it, like for example, Google deletes your browsing history, I think every 90 days. Um, you should be able to do that. If you want to leave a digital legacy to your kids, you should be able to do that. And yeah, so right now, Surfer Protocol consists of a desktop app that essentially handles all the exporting, a Python package which allows you to do stuff with that data, and a cookbook which are just example. It includes example applications that can hopefully give people some inspiration on what to build off of with Surfer. So I'll give you guys a quick demo. Um, can you guys see this?
Yep, we can see.
Yep. Perfect. Okay, yeah, so this is a desktop app. Here's sort of all the platforms I have. And the cool thing is, no matter how messy the exports are, like for example, Gmail does it in some mbox format that you have to parse through. It all comes back in a unified JSON schema that looks like this, where you have your sort of company name, run ID, timestamp, and then the content array. Hold on 1 second. Yeah. So that's really cool. And sort of the way the data is exported, it happens in different ways. So for some of them, like Notion and LinkedIn, what's essentially happening under the hood is intercepting the network requests that are made uh, within the platform's internal API, taking the cookies and then using that to make requests on the user's behalf. So I can show you guys Notion, for example. So what's happening here is it'll go to the Notion sort of home page, and in the background it'll be intercepting the Notion API token, and then it'll be making this export for me on my behalf. Um, and that's super cool. For some other ones, we will click and um, automate the clicking and scraping process. So for example, for the ChatGPT export, what would happen is would click the export button, go to your email, and then wait for that email. So that's super cool. And then also for iMessage, which surprisingly works on both Windows and Mac. Um, what we're able to do on Windows is if you back up your phone to your computer, you can essentially just, there's a Python library that we use to decrypt your iMessages. So here I have over 60,000 of my iMessages, which is super cool. And on Mac, there's a SQLite DB file that can be used. So that's pretty cool. And as for what you can do with this data, if you're a developer that wants to build applications, here's an example chatbot. Just your simple chat with data. And so what I can do is I can interact with my data, my Notion data. So if we look at the code here, all that's happening is it's just getting my Notion data, um, and then just iterating through it and then sort of adding it to the vector database. Obviously, this can be traded out for a local first option. I know SQLite Vec was on here a few weeks ago, so that could definitely be used in this case. But if I ask this, what is Surfer protocol? It should be able to know just based on my Notion data. And yeah, so that's just an example of sort of an application you can build off of, um, build with your Surfer data. Sort of the next steps for a project like this are so yesterday Claude's model context protocol came out, so that's some super cool stuff that definitely want to mess around with and see how server can work very well with that. Because the thing about something like Claude's MCP is that while it makes it easier to connect your data with LLMs like Claude, it doesn't mean that exporting that data is any easier. And I think that's where Surfer can really play a role, where things like iMessage or your entire Notion workspace, where these companies don't want to necessarily make it the easiest and most parsable. That's where something like Surfer can definitely come in. And I'll drop these links, but if you want to sort of support the project or just chat about it at all, here's some links here. And yeah, thank you guys for listening to my talk.
It's a good talk, Sahil. And like it's inevitable, like at some point data inversion will happen because the users are the common denominator across all of these silos. It's one of my biggest passions and why I'm also working on Vela. Like you mentioned, MPC, it's a way to provide context for ML systems. We had Open Devon that came out like when Devon announced their project, and Open Devon project got set up, and it's like got 30,000 stars since April, and basically it's trying to do an open source agentic framework. So you mix all of these things is like, what could you do if you had all your personal data from all of your Facebook, Instagram, LinkedIn, YouTube, whatever, and then have that structured and organized and ready to enhance your personal internet experience, as opposed to maximizing ransomware business models by these Web2 companies. Uh, on that very upbeat note for let's take ownership of our data, I will hand it over to Joshua, who has been working on Laurel. It's highly regarded, and I can't wait to learn from you, man. Take it away. Your mic is muted right now. If you want to go unmute.
Okay.
I
Sorry.
got you.
Okay. I'm gonna share screen. And my slides is available online.
Thanks. Is it collaborative?
No yet.
Guys, I'm joking.
Okay. Can you see my screen?
Yep, you're coming in great.
Okay, thanks. Hi everyone. It's an honor to be here and share our work with you. Let me briefly introduce myself. I'm Zixuan Chen and currently working on Loro.dev, a CRDT library that makes building local first app easier. And before this, I work on rich text editors at Lark, and you can find me on GitHub and Blue Sky. Let me walk you through what Loro is and why we created it and its feature, usage, and difference from other CRDT library, and peek under the hood at how it works and where we are heading next. So Loro is a CRDT library like YJS and AutoMerge, and Loro is designed to make your app state collaborative, and it offers various data types that are compatible, composable, and can be used to model JSON data structure. And it also comes with built-in version control. So what are CRDT? And maybe I don't need to introduce because in previous talk already covered this part. So CRDT are collaborative data types. If different peers apply the same set of operations, they'll always end up in the exact same state. And it enables local first experience. So let's look at code example to understand how to work with CRDT in Loro. So it's easy to sync text editing in Loro. Now imagine we have two peers that need to synchronize their states. And we can simulate two peers in physically different places here. And first we insert, first in doc 8, we insert hello, and doc B we insert hi. And they can export update via doc.export API, and you can use the delta update here to only include the updates that the other peer doesn't have. Then they can exchange those bytes via any channel and import the bytes from the other peer. And finally, both doc will end up in the same state because we assign each peer IDs, so the merge has deterministic result. Okay, you can also model JSON documents by using composable data types in Loro. It has all the types exist in JSON like lists, map, text, and so on. And you can export or import the doc by exporting import method. So why we created Loro? First is building collaborative experience is hard. I previously worked on collaborative software where the team invested significant effort in synchronization and collaboration, and we even once suffered user data loss due to improper implementation of collaborative algorithm. And second, maintaining data security is hard. The security contains two parts. One is availability. Even high SLA isn't enough. How can we ensure user data remains accessible after a company shuts down? This creates high transaction costs and often raise doubts about software from small teams. And there is privacy issues. Small teams often struggle to isolate development and operation staff from sensitive user data, while non-CRDT collaboration algorithms typically require plain text on the server side. And I found CRDT can also solve both of these issues. First is always available offline and supports switching between different sync servers and maximizing availability, and also makes end-to-end encryption, end-to-end encrypted real-time collaboration feasible. Also, I resonate deeply with local first software principles, and I believe it will become a crucial paradigm in the future. And as one of the foundational technology behind local first software, CRDT have great potential, and many achievements only exist in the paper at the time, but only a few were building production-ready CRDT libraries. So I started researching this direction 3 years ago, which led to Loro. So what's the difference between Loro and the existing works? we've been learning a lot from the existing work like AutoMerge, YJS, and especially Egg Worker and Diamond Type, while adding unique features and optimization. Our architecture allows for easy extension of CRDT types while maintaining high performance and version control compatibility. Loro currently supports a variety of CRDT types like movable tree, enriched text, movable list, map, counter, and it's extendable. Our architecture makes it easier for Loro to extend support for other CRDT types in the future. And it can maintain the forward and backward compatibility, but the functionality may be limited when an older Loro import documents from a new one. Loro's architecture is heavily inspired by Egg Worker. I will briefly introduce how Egg Worker works in the following talk. And it provides significant performance benefits through lazy loading, CRDT-related data structure, and efficient local operations. It also comes with lower memory overhead and faster document loading, and it brings Git-like shell clone. So how does performance look like? So in Loro, the performance isn't an afterthought. We've used various optimization techniques learned from other CRDTs. So we learned the operations merging optimization from YJS and efficient encoding format, the calendar encoding from AutoMerge, and lazy loading CRDT data structure from Egg Worker or Diamond types. We also borrow the idea of LSM tree, which make Loro 30 times faster in the benchmark on this slide. So in this benchmark, we import a doc with 25 million operations, and the final doc has over 10 million characters. Based on this benchmark, Loro remain responsive even for the most time-consuming tasks like importing and exporting. So the import only takes 16 milliseconds, while export takes 100 milliseconds, to 200 milliseconds. So another great feature of Loro is its version control. We've made a Loro version controller demo that import the entire Git history of Loro project itself. As you can see in the screen, you can seamlessly scroll between different versions in real time. I will introduce a few primitives in Loro that make this work. So here's an example about how you can switch to a different version, fork from it, and merge in Loro. First, we insert the text "Hello World" here, and each character insertion has its own operation ID as marked in this diagram. And then we can switch the document to an older version by calling checkout. So here we check out to the operation ID where the PA is 0 and the counter is 5. So right now the head is here. So we move the head to here. It means any operation ID with counter greater than 5 are excluded. So the text after the comma is excluded. Then the doc state is hello. And one way to branch off the current version is we can call fork to create a new doc at the target version. And then we insert Alice at the end of the text. And the state of the new doc thus become hello Alice. So here we have two different so it forms a directed acyclic graph like Git. So how shall we merge the two branches? We can import the changes. from the new version into from the new doc into the doc. So here we export all the updates from the new doc, and in doc we import those bytes. So here we call doc checkout to latest. We need to call this one because before we calling this method, the doc is still at this version. So the latest version is this two. So we have so we have two heads here. So it's a valid state in CRDT, although it's not a valid state in a version control system like Git, because CRDT can automatically merge those concurrent updates. So the final result is hello world Alice. It also has deterministic results because we assign the peer ID previously. So how does LoRa work? LoRa built upon an architecture inspired by EggWorker. It's a new collaborative algorithm that combines the best of OT and CRDT. Due to the time constraint, I will focus on two key aspects. First is how EggWorker combine the best of OT and CRDT, and how LoRa leverage its key insights. And the second part is our optimization that make import 10 times faster. So EggWorker is an algorithm presented by Joseph Gentle and Martin Klebman in the paper Collaborative Text Editing with EggWorker, Better, Faster, Smaller. It combines the advantage of both OT and CRDT, as you can see in this slide. First, CRDT has high memory overhead and slower import because it has more metadata, and also CRDT is kind of slow for local operations because you need to query and modify those metadata. In OT, you have lower memory overhead and fast document import and no overhead for local edits. So, but EggWorker took this advantage from OT, and also it remains decentralized like a CRDT. Also, it's fast in EggWorker to merge long concurrent edits, but OT will suffer from that. So this is so EggWorker algorithm doesn't need to load the whole data structure of CRDT into memory by default. So by default, it only needs the current state of the document. It doesn't need to construct those CRDT related data structure by default. So instead, it only construct temporary CRDTs when you encounter concurrent edits that need to be merged, like this example. So we have Alice and Bob. They concurrently insert different texts, and they need to be merged. So in this case, a temporary CRDT will be built, and it will calculate the diff that need to be applied to the document. And after you apply those after you apply the diff to the document, the temporary CRDT can be discarded. So, so that's why it's very fast for local operation, because it doesn't need to modify those CRDT related metadata. It only needs to change the local state of the document, and only need those CRDT data structure to be constructed when there are concurrent updates that need to be merged. And it only needs to extract those concurrent updates from the history. So here is a DAG, the history DAG. If it describes the causal dependencies between the operations. So egg worker only needs to load these updates from the from the history. It only needs this to construct the temporary CRDT. So it's very efficient. Claiming that Loro implements egg worker may be controversial, as there are many differences between Loro and egg worker in implementation detail. Nevertheless, Loro is greatly inspired by egg worker algorithm. For example, egg worker has clear separation of history and state. This separation in the architecture make a lot of things easier. For example, building the version control feature. And we also borrow the idea that CRDT data structure can be lazy loaded when using an algorithm like egg worker. And it makes time to interaction much faster and brings lower memory cost because we don't need to pass and store those CRDT data structure. And it has faster local operation. Egg worker is well implemented in diamond types. Use a B tree to handle the tag CRDT operation is very fast, and almost all operations are within n-log n time. We also done a lot of work to enhance and leverage the egg worker-like architecture. We made a dedicated algorithm design to extend the egg worker-like architecture to support rich tags, movable tree, and movable list. And we've also introduced additional data structure to make version switching fast. Furthermore, we introduced an innovative optimization technique that allows CRDT document to be loaded in chunks, resulting more than 10 times improvement in import speed, which we'll elaborate on below. So how does lazy loading work? So this part I'll cover the part about how we achieve the 10 times faster document loading. In egg worker, the editing history. I need to introduce a bit of a background. So in egg worker, the editing history is equivalent to the CRDT metadata in traditional CRDTs. The main overhead of egg worker comes from the editing history component. So when we have separate egg worker has separable history and state, and we can choose to save just the editing history and the editing history and the current document state, and it also supports shallow clone. Okay, this page of slides is kind of messed up. Sorry. So why we can lazy load history and state of the CRDT document? The insight is that we don't always need the whole past history and state. So the background is we have the separable history and state in the egg worker like architecture, and we have editing history as one part and the state as another part. When storing this data structure, and when storing those the when storing the document, we can choose to only store a part of the history, or a part of the state and a part of the history, and we suppose the shallow clone just like it, and this corresponding to the update format and snapshot format in Loro. So why we can lazy load the history and the state? Because the insight is we don't always need the whole past history and state. For example, the server may only need to import the snapshot uh, to get a slice of the update. In this case, the state doesn't need to be passed, neither the unwanted update. And when a client opens a document, it may only need to load a partial of the state. In this case, the unwanted state and the history don't need to be passed. To leverage this design, we need to split the history and the state into chunks when we store them. So how to implement this? So we learn a lot from LSM tree, a common data structure in key value database, and apply this lesson to low storage format. It allows us to only pass the actual used content. However, we still need complete binary content to be loaded into memory for now. Internally, Loro's storage format relies on a key value database abstraction, making it easier to implement true trunked loading and storage from disk or network in the future. So these benchmarks come from the egg worker paper, and it compare the import speed. So the numbers here are in milliseconds. So in this table, you can see Loro is much faster than AutoMerge and YIs when using the snapshot format, but it's still 5 to 10 times slower than diamond type. It's because Loro has additional data integrity check, and it uses a full snapshot. So while Loro's performance is already practical here, but there is still room to optimize further in the future. The egg worker architecture also made shallow clone easier to implement in Loro. It working similarly to Git shallow clone. So with shallow snapshot, user can remove redundant history, store those complete editing history in a cold storage, and use partial history in most cases for better performance. And since the main overhead in egg worker comes only from the edit history costs, after using shallow clone, its performance, like storage, memory, and operation speed, becomes comparable to working with low document directly. The performance benefits are significant. However, the limitation is that the user cannot merge remote edits that is concurrent to the trimmed history. So here is an example. So by using the shallow clone, the import speed can be 3 to 6 times faster. This benchmark is based on the data provided by LoFi.so. So what's our future plan? The development experience we hope to create is that the developers only need to manage their local state well and effectively use the primitives like collection sync, room, and presence, and data then can automatically synchronize and enable real-time collaboration while supporting end-to-end encryption. In development, have a complete editing history can help debug easier, but it requires a inspector. We'll work on that in the future, in the near future. An issue always it should also be easy to switch between different synchronized environment, which brings more freedom for both developer and end users. However, we are still far from the ideal developer experience, especially regarding the deployment. Therefore, in the future, we will collaborate and integrate with more tools such as the front-end state management tool and P2P networking and end-to-end decryption, and also the backend solutions like Cloudflare, Durable Objects, Supabase, and InstantDB. Okay. We also attempt to build a consumer application that brings a collaborative experience into user-friendly, familiar tools such as Obsidian and VS Code. We hope to bring the Notion and mirror-like experience to file system-based workspaces. It gives users more control and transparency while making version control accessible to non-technical users. This application will inherently possess the benefits brought by various CRDT features, including bidirectional synchronization across multiple different backends and supports the end-to-end encrypted synchronization method. You can apply for the early access here. It's called LoLoHub.com. And we hope to make it extensible as CRDTs like Lolo can flexibly model the data of JSON documents. And third-party developers can also extend the capabilities of the workspace based on the same protocol, enhancing the developer experience. Okay. So it's the end of my talk. Okay, thanks everyone.
My mind is officially blown. Great job, Jeshwan. And I'm sure everybody on the call has just been like furiously taking notes and trying to get everything down. I'm gonna stop the recording and the broadcast so that we can all hop on stage and ask questions, meet, chat. This community is really anchored by getting to meet each other in these conferences and also being able to kind of know someone beyond their